Question 1. In the context of system performance analysis, a walk-in freezer shows consistent coil frosting near the expansion valve while suction pressure remains lower than expected. The superheat is significantly higher than design values. What is the most likely cause? A. Excessive refrigerant charge. B. TXV sensing bulb lost thermal contact. C. Condenser fan failure. D. Receiver outlet restriction. Answer. Correct answer. B. Explanation. A sensing bulb losing thermal contact causes the TSV to misread coil outlet temperature under feeding refrigerant. This results in higher superheat and low suction pressure. Excessive charge would raise head pressure, not lower suction significantly. A failed condenser fan elevates head pressure, not superheat. Receiver outlet restriction would cause low suction and head pressures, but not localized coil frosting near the valve. Proper bulb placement and insulation per manufacturer specs prevents this fault. Question 2. When analyzing a medium-temp refrigeration rack, an operator notes the head pressure is stable but liquid line temperature is warmer than ambient. Sight glass shows bubbles under load. Which adjustment should be prioritized? A. Increase condenser water flow. B. Check subcooling and add refrigerant if low. C. Adjust evaporator fan speed. D. Replace the suction filter dryer. Answer. Correct answer. B. Explanation. Bubbles in the sight glass with warm liquid line suggest insufficient subcooling, indicating low refrigerant charge or flash gas formation before the metering device. Adding refrigerant to achieve target subcooling corrects the condition. Increasing condenser water flow affects head pressure, not subcooling if already stable. Evaporator fan speed changes heat load but not liquid line flashing. Suction filter dryer replacement addresses suction contamination issues, not liquid flashing. Question 3. By evaluating two parallel compressors in a supermarket rack, technician Alex finds one unit short cycling on low pressure cutout while the other runs steadily. Discharge temperatures are within limits. What should be investigated first? A. Oil return issues. B. Defective crankcase pressure regulator. C. Uneven evaporator load distribution. D. Suction service valve partially closed. Answer. Correct answer. D. Explanation. A partially closed suction service valve starves one compressor, causing rapid pressure drop and short cycling. The other compressor continues normal operation, masking the issue. Oil return problems would cause lubrication issues over time, not immediate short cycling. A faulty crankcase pressure regulator affects startup load, not steady state cycling. Uneven load distribution impacts suction balance but wouldn't cause single compressor to cycle rapidly without other symptoms. Question 4. In light of recent developments in refrigerant regulations, technician Maria is replacing R404 in a low-temp system with a WDW alternative. The POO is compatible, but the manufacturer advised TSV adjustment. Y8. New refrigerants always require lower superheat settings. B. The new refrigerant's pressure temperature curve affects flow rates. C. Oil return rates are reduced with WLEDs. D. Expansion valve power elements are compatible with POO. Answer. Correct answer. B. Explanation. Different refrigerants have distinct pressure-temperature relationships and density, which alter the mass flow through the TSV. Adjusting ensures correct superheat and coil performance. Not all refrigerants require lower superheat. Oil return is influenced by velocity and miscibility, not directly the refrigerant change in this case. Power elements relate to refrigerant sensing, not oil type. Following retrofit guidelines ensures compliance and performance. Question 5. The primary reason for an abnormally high discharge temperature in a hermetic compressor despite normal suction superheat and head pressure is likely due to A. Liquid floodback. B. Discharge line restriction. C. Low refrigerant flow causing higher compression ratio. D. Overcharged condenser. Answer. Correct answer. C. Explanation. Reduced refrigerant mass flow increases compression ratio, raising discharge temperatures even if suction superheat is normal. Liquid floodback cools rather than overheats the compressor. A discharge restriction raises head pressure and may trip high pressure controls, but doesn't cause isolated temperature elevation. Overcharging condenser elevates head pressure and may impact efficiency but isn't the direct cause here. Correct refrigerant flow ensures compressor longevity. Question 6. When faced with a flooded evaporator in an ammonia refrigeration system, operator Liam observes rising suction pressure and reduced discharge superheat. What is the immediate operational concern? A. Risk of liquid carryover damaging the compressor. B. Loss of oil return to the compressor. C. Reduced evaporator heat transfer capacity. D. High condenser water usage. Answer. Correct answer. A. Explanation. Flooded evaporators can carry liquid refrigerant into the compressor, causing mechanical damage due to liquid sliving. Oil return is a concern but secondary to preventing compressor failure. Heat transfer may initially increase in flooding conditions until liquid reaches the compressor. Condenser water use is unrelated. Ammonia systems require careful liquid level control to protect equipment. Question 7. Considering the evidence from a system performance log, the approach temperature in an air-cooled condenser has increased by 10 nF over the past month, while ambient conditions remain similar. What is the most probable cause? A. Refrigerant undercharge. B. Airflow restriction due to debris. C. Liquid receiver undersized. D. TXB oversized. Answer. Correct answer. B. Explanation. A higher approach temperature with stable ambient conditions typically indicates reduced heat rejection capacity, often from blocked condenser fins or fan issues. Undercharge lowers subcooling but not directly. Approach temperature if head pressure remains high. Receiver sizing affects storage but not daily. Approach temperature. TSV sizing affects evaporator feeding, not condenser performance. Regular coil cleaning maintains efficient heat exchange. Question 8. With respect to preventive maintenance, technician Sophia schedules periodic oil analysis for a screw compressor. What is the main diagnostic advantage? A. Detecting moisture content in refrigerant. B. Identifying early mechanical wear and contamination. C. Verifying superheat calibration. D. Measuring coil surface fouling. Answer. Correct answer. B. Explanation. Oil analysis reveals metal particles, acids, and sludge, indicating bearing wear, overheating, or contamination before catastrophic failure. Moisture in refrigerant is detected via other tests, such as acid or moisture indicators. Superheat calibration involves field measurements, not oil testing. Coil fouling assessment requires physical inspection or airflow testing. Regular oil analysis extends compressor life and ensures reliability. Question 9. Through the lens of electrical troubleshooting, technician Daniel finds a refrigeration unit's contactor coil repeatedly burning out within weeks. Voltage matches nameplate, but coil life is short. Which factor is most likely? A. Undersized coil wire in contactor design. B. Excessive harmonic distortion from nearby equipment. C. Incorrect refrigerant charge causing overheating. D. Poor crankcase heater operation. Answer. Correct answer. B. Explanation. Harmonic distortion from variable frequency drives or other electrical noise sources can overheat coil windings, shortening life despite correct voltage. Undersized wire is a manufacturing defect and unlikely if OEM supplied. Refrigerant charge issues don't directly affect control coil life. Crankcase heater issues impact oil temperature, not electrical component lifespan. Mitigating harmonics may require line reactors or filters. Question 10. Given the circumstances of a walk-in cooler with fluctuating box temperature, the defrost timer is set for 4 cycles per day, but frost still accumulates. Drain pan heater works correctly. Which adjustment is most logical? A. Increase defrost duration per cycle. B. Lower thermostat cutout point. C. Reduce evaporator fan runtime. D. Replace liquid line solenoid. Answer. Correct answer. A. Explanation. If frost persists despite correct cycle frequency, extending defrost duration allows complete meltout, preventing residual frost from growing. Lowering thermostat cutout affects product temperature, not frost buildup. Reducing fan runtime impacts air circulation and load control, but not root frost accumulation. A faulty liquid line solenoid would cause temperature rise, not frost persistence. Corrective ensures airflow and heat transfer efficiency. Question 11. During the process of commissioning a large cold storage facility, technician Marcus observes that the liquid line temperature is consistently 12 degrees above ambient despite adequate subcooling readings. What is the most probable issue? A. Liquid line insulation deterioration. B. Expansion valve oversized. C. Receiver overfilled with refrigerant. D. High condenser fan cycling rate. Answer. Correct answer. A. Explanation. Damaged insulation allows heat gain into the liquid line, raising its temperature above ambient even if subcooling appears adequate. Oversized SBS impact evaporator feeding, not liquid line temp directly. Overfilled receivers elevate head pressure but wouldn't cause constant temperature rise independent of load. High fan cycling affects condenser efficiency but not liquid line heat gain. Proper insulation reduces unwanted heat absorption and maintains system efficiency. Question 12. From a practical standpoint, technician Elaine is troubleshooting a blast freezer that struggles to reach set point. Suction pressure is higher than design, superheat is near zero, and frost is visible on the suction line to the compressor. What is the root cause? A. Undersized evaporator coil. B. Liquid floodback from overfeeding EXP. C. High ambient temperature. D. Excessive condenser surface fouling. Answer. Correct answer. B. Explanation. Zero superheat with frost at the compressor suction indicates liquid refrigerant returning to the compressor, usually from an overfeeding ESP. An undersized evaporator causes high load but not frost on the suction line. High ambient temperature increases condenser load, not suction flooding. Surface fouling on the condenser would raise head pressure but not cause liquid floodback. Correct. EXP adjustment protects life and efficiency. Question 13. The underlying principle of oil separators in large industrial refrigeration systems is to A. Prevent oil from reaching the condenser and fouling coils. B. Keep oil in the compressor crankcase by blocking flow. C. Capture and return oil to the compressor to maintain lubrication. D. Allow oil to circulate freely for heat transfer purposes. Answer. Correct answer. C. Explanation. Oil separators remove oil mist from discharge gas and return it to the crankcase to maintain lubrication and prevent oil logging in evaporators. Preventing oil from reaching the condenser is a partial benefit but not the main function. Blocking oil flow entirely would cause compressor failure. Allowing oil to circulate freely increases risk of poor heat transfer and maintenance issues. Oil management is critical for long-term reliability. Question 14. As illustrated by a supermarket parallel rack system, one compressor consistently runs at higher oil temperature than the others despite similar load conditions. What should be checked first? A. Oil cooler operation. B. Crankcase heater control. C. Suction filter condition. D. Liquid injection system. Answer. Correct answer. D. Explanation. Many racks use liquid injection to cool compressor discharge gas and reduce oil temperature. Failure in the liquid injection circuit will raise oil temperatures in their compressor. Oil cooler operation is relevant in systems designed with them but less common in smaller racks. Crankcase heaters affect oil temperature during off cycles, not operation. Suction filters influence pressure drop, not oil overheating directly. Question 15. In comparison with normal startup conditions, a chiller shows abnormally slow pull-down time. Suction pressure drops gradually, head pressure is normal, and amperage draw is lower than expected, which is most likely A. Compressor valves leaking. B. Evaporator water flow too low. C. Excessive superheat setting. D. Refrigerant overcharge. Answer. Correct answer. A. Explanation. Leaking compressor valves reduce volumetric efficiency, slowing cooling capacity and lowering amperage draw due to reduced load. Low evaporator water flow would cause freezing or high DT, but not low amperage directly. Excessive superheat reduces coil utilization, but usually shows in pressure readings more clearly. Overcharge raises head pressure and amperage, not lower it. Valve integrity is crucial for performance. Question 16. According to recent studies on system efficiency, excessive compressor cycling in a region cooler leads to which primary inefficiency? A. Reduced oil return efficiency. B. Increased electrical and rush losses. C. Excessive condenser fan cycling. D. Overfeeding of the evaporator coil. Answer. Correct answer. B. Explanation. Frequent compressor starts cause repeated high inrush currents, reducing overall efficiency and stressing electrical components. Oil return is a concern but not the main energy and efficiency here. Condenser fan cycling is influenced by head pressure control, not compressor cycling. Overfeeding is related to metering device control, not start-stop frequency. Properly set controls minimize cycling and improve energy efficiency. Question 17. Examining the consequences of a faulty evaporator pressure regulator (EPA) in a multi-evaporator low-temp system, what operational symptom is most likely? A. Overcooling of high-temperature zones. B. Uneven compressor oil levels. C. Flooding of the condenser. D. Excessive suction pressure in the controlled circuit. Answer. Correct answer. D. Explanation. A faulty EPA that fails open allows suction pressure in the controlled circuit to rise above design, reducing dehumidification and potentially increasing product temperature. Overcooling occurs if the valve fails closed in a high temp zone. Oil level imbalance is unrelated to EPA function. Condenser flooding is more related to head pressure control or liquid management issues. EPAs protect temperature control in multi-zone setups. Question 18. In a modern context of a DOE refrigerants, technician how it notices increased compressor discharge temperature after retrofitting from R22 to R448 even though superheat is within spec. What is the likely reason? A. Higher specific heat of R448. B. Increased compression ratio from lower vapor density. C. Oil type incompatibility increasing friction. D. Expansion device malfunction. Answer. Correct answer. B. Explanation. R448 often results in a slightly higher compression ratio due to its thermodynamic properties, which raises discharge temperature. Specific heat alone doesn't cause significant discharge temp changes. Oil incompatibility can cause wear, but not immediate discharge temp increase if miscibility is maintained. Expansion device malfunction affects coil feeding, not compression ratio. Retrofits require checking compression ratios to avoid overheating. Question 19. By comparing defrost control strategies, technician Prayer considers converting a freezer from time-initiated to demand defrost. The primary performance improvement would be A. Reduced frost accumulation per cycle. B. Increased defrost duration for complete melt-out. C. Reduced energy consumption from fewer defrost cycles. D. Lower evaporator air velocity during defrost. Answer. Correct answer. C. Explanation. Demand defrost triggers only when frost accumulation reaches a set threshold, reducing unnecessary defrost cycles and saving energy. Reduced frost accumulation is a result, not the main performance gain. Increasing duration increases melt-out but not efficiency if unneeded cycles occur. Lower air velocity during defrost isn't the primary efficiency factor. Demand-based control optimizes both performance and energy use. Question 20. Under the assumption that a technician is replacing a semi-hermetic compressor in a rack system, which step is most critical before introducing refrigerant? A. Pulling a deep vacuum to remove non-condensables and moisture. B. Adding oil directly into the suction line. C. Purging the system with nitrogen while operating the compressor. D. Bypassing the oil separator temporarily. Answer. Correct answer. A. Explanation. Removing all non-condensables and moisture is vital before refrigerant introduction to prevent acid formation, corrosion, and efficiency loss. Adding oil via suction line is done when charging oil but is not the main pre-refrigerant step. Purging with nitrogen is part of brazing prep, not final evacuation. Bypassing the oil separator risks improper lubrication and is never a pre-start step. Proper evacuation ensures system longevity in compliance with best practices. Question 21. When considering a cascade refrigeration system, technician Omar notices the high stage condenser subcooling is low while head pressure is within the expected range. What should be the first investigation? A. Verify refrigerant charge in the high stage. B. Inspect low stage evaporator fans. C. Check oil return from the low stage. D. Measure defrost heater amperage. Answer. Correct answer. A. Explanation. Low subcooling in the high stage often points to insufficient refrigerant charge. Even if head pressure is normal, charge deficiency reduces liquid cooling capacity before expansion. Low stage fan issues affect the other stage load, not its subcooling directly. Oil return problems are critical but unrelated to subcooling readings. Defrost heater amperage is irrelevant to condenser performance during normal operation. Question 22. Throughout the course of the seasonal maintenance, technician Liam measures elevated condenser approach temperature and abnormally high compressor amp draw on an air-cooled chiller. What is the most likely cause? A. Evaporator fan motor failure. B. Non-condensables in the system. C. Liquid line solenoid valve failure. D. Undersized receiver. Answer. Correct answer. B. Explanation. Non-condensables raise condensing temperature and pressure, increasing approach temperature and compressor workload. Evaporator fan failure affects evaporator load, not condenser approach. A failed liquid line solenoid impacts refrigerant feeding, not condenser performance directly. Receiver size affects storage but not approach temperature. Purging and proper evacuation prevent non-condensable buildup. Question 23. Contrary to popular belief about liquid line filter dryers, technician Maria replaces one in a small reaching cooler and sees no improvement in pressure drop. What is the correct interpretation? A. System still has a restriction elsewhere. B. Compressor is losing efficiency. C. Evaporator coil has excessive frost. D. TXV sensing bulb is misplaced. Answer. Correct answer. C. Explanation. If replacing the filter dryer does not resolve pressure drop issues, the cause may be unrelated, such as excessive evaporator frost restricting airflow and heat transfer. A separate restriction could exist, but frost blockage is common in smaller units. Compressor inefficiency causes capacity loss, not pressure drop across the filter dryer. A misplaced sensing bulb affects superheat control, but not liquid line pressure directly. Question 24. During the process of diagnosing uneven temperatures in a multi-zone refrigeration system, technician Jorge finds that one's own HEPA valve outlet temperature is nearly equal to its inlet. What is the likely cause? A. Valve stuck fully open. B. Liquid line partially blocked. C. Evaporator fan blades damaged. D. Incorrect defrost termination setting. Answer. Correct answer. A. Explanation. If an HEPA valve is stuck open, the outlet temperature will match the inlet because the valve fails to maintain the design pressure drop. A partially blocked liquid line impacts feeding but not the HEPA's pressure control behavior directly. Damaged fan blades reduce air distribution, not valve performance. Defrost termination settings affect coil frost control, not HEPA pressure differential. Question 25. The growing trend in retrofitting older R22 supermarket racks to blended refrigerants often results in what operational challenge? A. Oil return at lower suction velocities. B. Reduced condenser surface efficiency. C. Oversized expansion devices. D. Increased motor winding temperature. Answer. Correct answer. A. Explanation. Many deduct pollens have different densities and flow rates than R22, which can reduce suction velocity, impairing oil return to the compressor. This can require piping modifications or increased load staging. Condenser efficiency is typically unaffected if heat rejection capacity is maintained. Oversized ESVS are possible but less common than oil return problems. Motor winding temperatures are more related to electrical and load factors than refrigerant choice alone. Question 26. By evaluating suction superheat trends over several weeks, technician Alex notices that values slowly climb above design despite constant load conditions. Which is the most likely cause? A. TXV loss in calibration. B. Suction filter partially blocked. C. Discharge line insulation missing. D. Receiver outlet check valve leaking. Answer. Correct answer. C. Explanation. Missing discharge line insulation increases radiant and convective heat gain into the refrigerant, leading to higher measured superheat over time. TXV miscalibration would cause abrupt, not gradual, superheat deviation. A blocked suction filter would lower suction pressure but not necessarily shows a gradual trend. Receiver outlet check valve leakage affects refrigerant migration during shutdown. Steady state superheat. Question 27. As a result of poor liquid refrigerant management, technician Prayer finds liquid refrigerant in the compressor crankcase during startup. What is the most immediate mechanical risk? A. Liquid slugging causing valve and piston damage. B. Overheating of motor windings. C. Premature oil breakdown from acid formation. D. Head gasket failure due to pressure spikes. Answer. Correct answer. A. Explanation. Liquid slugging occurs when incompressible liquid enters the compressor cylinders, potentially damaging valves, pistons, and connecting rods instantly. Overheating of windings is usually caused by electrical or airflow issues. Oil breakdown from acid is a long-term chemical issue, not immediate. Head gasket failures are rare compared to direct impact damage from slugging. Question 20. Focusing specifically on the effects of undersized suction lines in large refrigeration plants, which is the primary operational impact? A. Lower compressor oil temperature. B. Excessive pressure drop reducing capacity. C. Increased refrigerant charge requirements. D. Overfeeding of the evaporator coil. Answer. Correct answer. B. Explanation. An undersized suction line increases friction losses, causing excessive pressure drop and reducing evaporator capacity and compressor efficiency. Oil temperature is not directly reduced by line sizing. Refrigerant charge may be slightly affected but not significantly. Overfeeding is a control or TXB sizing issue, not pipe diameter related. Proper line sizing per ASHRAE guidelines is essential for capacity. Question 29. When evaluating the merits of electronic expansion valves EVs over thermostatic ones in low-temp systems, which advantage most directly improves product temperature stability? A. Continuous modulation of refrigerant flow. B. Lower installation cost. C. Reduced oil migration. D. Simplified manual adjustment. Answer. Correct answer. A. Explanation. EVs can modulate refrigerant flow based on precise temperature and pressure inputs, providing tighter control over evaporator superheat and maintaining stable product temperatures. Installation costs are typically higher for EVs. Reduced oil migration is a possible benefit, but secondary. Manual adjustment is simpler with TSSVS or EVs. Stability is improved through continuous flow control. Question 30. The conventional wisdom about suction accumulators is that they protect compressors during floodback events. What is their actual key operating principle? A. Temporarily storing liquid refrigerant and allowing vapor return. B. Evaporating liquid refrigerant using crankcase heaters. C. Maintaining constant suction pressure during load swings. D. Preventing refrigerant migration during shutdown. Answer. Correct answer. D. Explanation. While suction accumulators do store liquid temporarily, their main protective function is to prevent liquid migration to the compressor during off cycles, especially in heat pump and low temp systems. Using crankcase heaters for evaporation is a different safeguard. Maintaining constant suction pressure is a regulator's role, not the accumulator's. Migration prevention ensures compressor startup safety.